We're into chapter 13. And last time, really, we were talking about how to solve ice tables and equilibrium problems. Remember again, when we do our ice table, we have our initial concentrations. The change part is really important. Again, typically speaking, minuses are on the left-hand side, pluses are on the right-hand side. And in addition, if there's any type of coefficient, we do also need to sort of take that into account when we do that part of it. That again takes into account the stoichiometry of it all. We would come down here, and really the goal of this calculation is to really figure out the change part, or the x value. And we could do that obviously with the quadratic formula and some other ways to solve these sort of problems. Once we do have the x value, we can go back into here. And obviously we get the x value by going into our K expression here, our products over our reactants. And obviously we have a K value given to us. And once we do that, we will have the equilibrium concentrations of everybody. As we talked about, typically speaking, molarity there for you're using concentration, and atmospheres if you're doing some type of pressure calculation, which again, by the way, you can do just like any other one. You just use pressures instead of concentrations. And you would probably be using the Kp value instead of the Kc value. Any questions on that there? So I think last time we were ending at this one here, and you're supposed to finish it and all that good stuff, which I'm sure you did. So we will go through this here together and see how we did. So here on this particular one, we do have the concentrations of everybody given to us. So we have our H2, our I2, and our HI. So we have some initial concentrations of each of those. We're looking for the K value here. We're looking for the equilibrium concentrations, and the K value here is 54.3. So the first thing that we really want to do in this case is, because we are actually given the equilibrium or the concentrations of everybody that is there, we would actually want to calculate Q in this case. And the reason we want to calculate Q, which is what we talked about previously, is Q is sort of what is known as the reaction quotient, is calculated the exact same way as you calculate K. The idea there is you're not sure if you're at equilibrium or not, so Q will tell you whether or not you're at equilibrium. I'm going to assume probably in this case that you're not at equilibrium, otherwise it wouldn't be much of a problem to calculate. But it will also help us, as we talked about, understand which way this reaction needs to go to reach equilibrium. And as we talked about, that's important for the change part of the ice table, and you're doing it so you know really which way this is proceeding. So the first thing we really want to do here is take Q, which again is the exact same way that we do K, and we'll do that squared divided by H2 and I2. And in this case, we're just going to put in the concentrations that were given to us. So here, thank you, the HI is 0.0224. Again, we need to square it. Divided by the H2 concentration, 0.00623, and our 0.00414. And if we put all that in, we will get 0.0224 squared divided by 0.00623, hit equals, divided one more time, 0.00414. And that's going to give us a, we'll call it 19.5. So remember here, we're going to compare Q to our K value that was given to us. And in this case, Q is less than K, which we would probably expect in the sense of we know we're probably not equilibrium again, otherwise there wouldn't be much to do. But more importantly, this tells us which ways it need to go to reach equilibrium. To the left, to the right, which ways it need to go? Yeah, so it's going to go opposite of where that's pointing. So it's going to head towards the product side, right? So now that we know that, we do and can feel comfortable to know that when we do the change part, the reactants should be our minuses and the products should be our pluses. Now, clearly, if we got the opposite here and I said it needed to go the other way, we would have to adjust our change part. And obviously, the reactants would be the positives in that case. and the products would be the negatives if it happened to come out the other way. So again, as we were talking about with Q, which I think was another thing that we talked about last time, this is another sort of spot where you would use Q. The reason we didn't even worry about it on the previous couple of problems that we did was there was no way to calculate Q because we weren't given the concentrations of everybody. So remember that you need the concentrations of everybody in order to calculate it. Any questions on that? Yeah. Yeah.
Is less than one, you will still get. Yeah.
If K is less than one, if the equilibrium constant is less than one, then you would get the idea K applies to any K value that you have. So yeah. Other questions? Okay. So now we could actually get into the calculation, which looks not fun, but we'll do it. Why not? All right. So we have here H2I2. All right. So we got a little H2 plus some I2 going to 2HI. And again here, initially we got for H2 0.00623. 0.00414 and 0.0224. All right, got all my numbers here. All right, so on this one, a little bit different because we are giving the concentrations to everybody. We're going to have an initial everywhere. The change part is going to be similar. We verified by calculating Q that it is heading towards the products, which means we should have minuses there on the left, and here we will have pluses. Once again, we do want to make sure we take into account the coefficient. That means when it is all said and done, 0.00623 minus x, 0.00414 minus x, and this is actually going to be 0.0224. This is going to be a plus 2x in this case. Any questions on this one here? All right, so like normal here, we can go into our equilibrium expression, which would be HI squared. And that's going to be H2 and I2 in this case. And as we saw in the previous problem there, 54.3 looks like a winner. So putting all that in there will get us 0.0224 plus 2x, and that's going to be squared, divided by 0.00623 minus x, 0.00414 minus x, is equal to 54.3. All right, fun time with math now, right? We're going to be taking a lot to sort of factor out. All right, so what I'm going to do is I'm going to actually kind of do the top part first. And then maybe I'll do the bottom part over here, and then we'll kind of put them back together and see what we end up with. So looking here first at the top part. So basically, that is basically 0.0224 plus 2x times 0.0224 plus 2x. And if we do our little factoring out there, we're going to get 0.0224 times 0.0224. We're going to get 5.018 times 10 to the minus 4. Don't know how too many zeros work in there. That's going to be plus 0.002, not too many zeros, 0.0224 times 2. 0.0448x. We're going to get another 0.0448x, and we're going to get a 4x squared. And again, that obviously is in and out, in and out. Yes. All right, so at this point, we're just going to combo this and kind of clean it up here. So for the top, we should end up with 4x squared plus 0.0448 twice 0.0896x plus 5.018 times 10 to the minus 4. Any questions on that one there? All right, I'm gonna do kind of the same thing here for the bottom one, and I'm gonna factor that guy out as well. And maybe I'll flop the page there so I got a little bit more room to do that. So 623 and 414. All right, so this is the bottom part here. If I copied it right, I think. Yeah, I got it. 623 414. All right, so again, we're going to go in and out here. And if we start that, we will end up with 0.00623 times 0.00414. Going to give us a 2.579 times 10. We got 1, 2, 3, 4, 5, I believe. Minus 5. Minus a 0.00623x minus a 0.00414x plus an x squared. Kind of combining our middle term there for the bottom here, going to give us an x squared minus 0.01037x, and that's going to be a plus 2.579 times 10 to the minus 5. Any questions on that so far? All right, so now I'm going to grab my equation there from the previous page and pop it back over here, I hope. So we have 4x squared. Oops. So 4x squared 0.0896. And 5018. And I believe these were all pluses, if I'm not mistaken, there on that page. Plus, plus, plus. Sounds good. All right, and then we'll take the bottom there that we just did. X squared minus 0.01037x plus 2.579 times 10 to the minus 5. And that's going to equal 54.3, which is our equilibrium constant value here. All right, so obviously we got a little bit more to go. We're going to multiply everything on the bottom to the other side there. And that's going to give us 4x squared plus 0.0896x plus 5.018 times 10 to the minus 4 will equal 54.3x squared minus 0.01037 times 54.3. 0.56309x plus and it looks like we'll go 1.40 times 10 to the minus 3. All right, lastly, we're going to bring everybody to one side. So I'm just going to choose to take everybody on this side and bring it over to this side just to keep the x squared positive. Again, you don't necessarily have to do that, but we'll do it in this case. So that looks like perhaps a 50.3x squared will give us 0.0896, basically plus that there. Minus 0.65269x, and that's going to give us minus 5.018 minus 4. And plus 8.98 times 10 to the minus 4 is equal to 0. Good so far? Yes, I hope. All right. I believe now we have, hopefully, some type of A, B, and C. We'll hope they're the right ones there. All right. Now we are ready to roll into our quadratic, which, you know, if you haven't given up on this problem yet, it will be something like 0.65269 plus or minus I'm just gonna kind of clean up what's inside this square root first. So I'm gonna go 0.65269 and square it. I'm gonna minus it by 4 times A, which is 50.3, times C, which is 8.98 to the minus 4. That's going to give me inside the square root like 0.245326. Upon square rooting it, gonna get me a 0.4953. 953. All gonna be divided by 2 times A, which is 50.3. That's 100.6. All right, so we'll do our positives first. There we go. 0.4953 divided by 100.6. Going to give us 0.0114. Now doing this subtraction, 0.65269 minus 0.4953 divided by 100.6, going to give us 0.00156. Any questions up to there? Yeah. All right, so we have our two values here. We need to check which one will be good. So I'm going to go back to our ice table. And frankly, I'm just going to steal some of this here so I don't have to rewrite everything. So we'll do all this and hope everything was good. All right, so going back to our ice table with our 2x values that we got. Let's see how we did here. All right, so 1x value was 0.0114 or 0.00156. In this case, this guy here is going to be too big, right? Because if we pop that back into there, we will get a negative value. So that's not good. So I'm going to roll with this one, which hopefully will not be too big. That means the concentration of H2 would be 0.00623 minus 0.00156. 0.00623 minus 0.00156. 0.00467. We're going to do our I2, which would be 0.00414 minus our X value. And that's going to get us 0.00414 minus 0.00156, 0.00258. And lastly here, this is going to be 0.0224. Remember that this one is actually a plus, not a subtraction. And that's going to be 2 times 0.00156. And that will get us here 2 times 0.00. If I hit the right number, that would be good too, probably. 0.0255 molar in this case. And dare I say, hopefully that should be the right thing. And that hopefully should be what you got as well. Yes. If we take these values once again and go back into here, we get like 54 and some change, which I'll take it, I think. Any questions on any of those steps? So a little bit more complicated of a quadratic, a lot more factoring happening there. Just got to be careful you don't lose some zeros, punch things in right, put it back together correctly. Might be a good idea to do that, kind of separate them and then put them back, just kind of keep track of everything that you do, put it back. Any questions on any of that there? Yes, sir. Yeah, so for example, in this particular case, we did calculate Q. So we know for this guy to reach equilibrium, this reaction has to head in this direction, which means over here, we should be adding that to it. And that's why it's plus. And it is a common mistake sometimes people make, because at this point, we're so used to kind of with the X's going minus X that you just kind of go autopilot sometimes. But it will be plus X on that side, yeah. Other questions? All right. So, and again, as we talked about earlier, if we did calculate Q and it was heading in the other directions, really the difference in our ice table is the plus and the minus would switch. Because it is actually written in this form as H2 and I2 on the reactants and HI on the products, we would not reverse our K value. Yeah. If you do reverse your K value, you then need to reverse the equation as well. So you got to keep that in mind. You don't want to kind of do that. So sometimes people think, for example, if it's heading in the opposite direction, oh, that's we kind of going the wrong way. I need to take 1/K and use it on the calculation. But if you do that, you actually do need to flip the actual equation and stuff like that. Or you can leave the K like it is and have it heading in that direction. Yeah. Yeah, several pages of calculation is absolutely wrong. Yeah. This is sort of where it is. This in a sense, yeah, people will sometimes obviously mess up on the calculation and stuff like this. But there is later on actually, if it's I don't know if it's encouraging or not, but next chapter is actually a place where that could happen. You'll do like really the wrong calculation rather than just messing up the calculation. Yeah. Exactly. And you would keep, so for example, the way the equation is written, if it was going in the other directions, you would swap the signs on the x's. You would keep the k the same as it is there, 54.3. Yeah, you could yeah, you could do the ICM exactly the same way, just swap the signs and do it the exact same way. It will come out the same. Yeah. What I'm saying is sometimes what people will do in that situation, and it doesn't occur a lot, by the way, we're talking about here, but what sometimes people will do is they'll go, oh, wait, my pluses are over here, my minuses are over here. They'll leave the equation exactly like it is. And instead of using the K value, they'll use 1/K, which then you'll get the wrong answer. You have to keep it with the same K value because you didn't actually switch the equation around. So if you do want to switch the equation, you got to take 1/K. Yeah. All right, more fun with math here. Here we go, one more. The KP in this case, 4.31 times 10 to the minus 4. Calculate the partial pressures or the pressures of each of these guys at equilibrium. If we started with 0.862 atmospheres of N2, 0.373 atmospheres of H2 in a constant volume at 200 degrees Celsius. So we got some pressures here, works the same way as concentrations. So ice table it up, see what you get. And we'll talk about it in just a bit. Okay, so let's take a look at this one and see how you're doing. So as I mentioned before, even though we have a KP given to us and we do have pressures, it really does work the same way as any other sort of ice table. Once again, make sure it is in atmospheres though before you go into the ice table. So in this case, our KP would be 4.31 times 10 to the minus 4. So our KP expression would be the partial pressure of NH3. And again, we would need to square it, divided by the partial pressure of N2 and the partial pressure of H2, which would need to be cubed. And again, that would equal our 4.31 times 10 to the minus 4. So we can go right into sort of our ice table. And again, we could use our pressures there the same way. So we'll do our, this case here, I think, what we got there, 0.862 for it into. So initially here we have 0.862, we have 0.373, and once again, no mention really of any pressure there on our product, so we could assume 0. Again, our K value here going to be partial pressure NH3 squared divided by partial pressure of N2, partial pressure cubed of H2, and 4.31 times 10 to the minus 4. All right, so the rest of the ice table here is going to be the same. We're going to go minus x. Remember, we do need to take the coefficient there, minus 3x, and also coefficient on this side, which would be plus x. This is going to go into our equilibrium here of 0.862 minus x, 0.373 minus 3x, and 2x. So taking this into our k expression there will give us 2x squared. divided by 0.862 minus x, 0.373 minus 3x. Oh, we got to cube that too. And that's going to equal 4.31 times 10 to the minus 4. Clearly, at this point, is there any question on the ice table or anything like that? At this point, we do need to solve it for x, and really the right choice is, go to the next problem. Probably is the right choice there, I think. But no, we won't do that. So we clearly want to think about how we could solve this, and there is a good way that you could kind of solve this, and it does involve the idea of our k value in this case. So our k value in this case, is it a large or small k value? It is a small k value. And because it's a small k value, that means that when we reach equilibrium, should we mainly have reactants or products? We should mainly have reactants. And because it is small and we should mainly have reactants, that means that the change part here, will that be a large change or a small change occurring? It'll be a small change. So in these situations where you have a small value of K, which means you basically have mainly reactants, you probably don't have a lot of stuff going from reactants to products in this case, and you have a small change. You can do what is referred to as making an assumption, and you could assume that X is equal to 0 in this case, as it is a very small change that's going to occur. Now, clearly in this case, you cannot assume that all X's are 0 because frankly, at that point, you have nothing to solve from. So the only X's that we assume that are 0 or anything that we're going to subtract it from a number are added to a number. And that's going to be the change that we're going to do that. The reason we would not zero out the top guy is starting at 0, right? So anything you get if you start at 0 is a pretty good change, right? Because you started with nothing. So we obviously can't zero them out. So in this case, the X's we're going to zero out are these X's right here. And that will reduce us down to basically 2x squared divided by 0.862 times 0.373 will equal our 4.31 times 10 to the minus 4. Now that feels like a lot easier of a thing to solve for. We also do need to cube that guy on the bottom as well. And that's what we're going to do. So I'm going to kind of get the bottom here and then multiply it over to the other side. So I'm going to take my 0.373, and once again, you do need to cube it. And I'm going to times it by 0.862. That'll give me something like 0.0447. We're going to multiply that to the other side, times 4.31 to the minus 4. And that's going to give me 4x squared on the left as I square the top there. 1.928 times 10 to a lot of zeros there. 1, 2, 3, 4, 5. I'm going to divide by 4, and then I'm going to square root it after I divide by 4. So I'm going to divide by 4, do a little square root action on it. And that is going to give me an x value here of, we'll call it 2.20 times 10 to the minus 3. Any questions on that there? So this way is a little bit easier of a way to solve these guys. Now, if you do make this assumption, you do need to check your assumption to make sure that it is okay. So whenever you do this assumption, you got to make sure to check it. So the way that we're going to check your assumption is we're going to use what is sometimes referred to as the 5% rule. And what the 5% rule is, you will take the x value that you got. So you'll take your x value that you got there, and you'll divide it by what you were going to subtract it from and times it by 100%. And if it's less than 5%, you're good to go. And if it's more than 5%, you have a little tear moment and you go back and probably solve it with the quadratic formula. So you should always check it though to make sure everything's good. It's like 0.25%. If you want to check both, you can, but in theory, if one works, the other one probably will work as well. But if you want to check them both, you can. So in this case, the check is good, which means our X value here is going to be the X value that we're going to use. And now we have what we need to obviously figure out our equilibrium concentrations there. Any questions on the assumption or how you check it? Why did I not use the assumption on any of the problems that we did previously? You could, but you could also use it on those as well. The reason, what's that? It is, but we didn't use the assumption on the previous ones because the K values were large, right? The K values were 54.3 and like 7.7 or something like that. And what those large K values mean is that the change is going to be relatively large going to the product side, and that we can't make that assumption. So you can only use this assumption when your K value is small, because the change should be relatively small. You should, like I said, always check it. It may not always work, so it might not be good. So that does leave you the option of, if you don't want to do the assumption, you could always kind of quadratic it. In our situation, is probably the most complicated you need to do. Or if you want to use the assumption, it can save you some time, but just make sure you do check it, because again, it may not always work. And you can only really apply this if the K value is on the small side. All right, so now that we have it there, I'm just gonna kind of squeeze in. Yes. Yeah, if it doesn't work, you would have to find some other way to solve it. And in our cases, probably that's gonna be just a basic kind of quadratic type thing that we've done previously to do that. I wouldn't give you one like this that wouldn't work. That you would have to go crazy with the math, I don't think. So we could go now back into, these are our pressures now in this case, and that's going to be 0.862 minus 2.2 times 10 to the minus 3. And that will get us 0.862 minus 2.2 to the minus 3. 0.8, I'll call it 60. And these are atmospheres, since these are pressures. Our partial pressure here of H2 will be 0.373 minus 3 times 2.2 times 10 to the minus 3. 0.373 minus 3 times 2.2 to the minus 3. 0.366. And lastly here, the pressure of NH3 going to be 2 times 2.2 times 10 to the minus 3. It'll give us a 0.0044 atmospheres in this particular case. Any questions on that particular one there? So at this point, we have now seen a number of ways that you can solve these problems. So for us, those are going to be basically the 3 ways that you can solve it. Maybe you get a perfect square. You can do a quadratic formula to solve it, or you can make an assumption to solve it. Once again, really the only way that we will not solve these, as I mentioned, I think last time, is by what's sometimes again referred to as successive approximation, which basically means, again, that like it's got to be less than that 0.862 number. You kind of put that in there for every x except for the 2x squared, and you solve it and get an x value, and you keep putting in numbers until the number you put in and the number you get out is the same. And again, that could be a really long day if it goes bad for you. So we won't do that, but sometimes books do solve these problems through successive approximation. Any question on equilibrium type calculations? Yes. Sure. Wherever it went. Here somewhere. This one, or yeah. Okay.
On the part you plug it back with the ice, how did you know that
Here.
the 0.01 close not really?
Yeah, so for example, if we just plugged it, say, back into this expression, which is what we would want to do with it, right? We would have 0.00623 minus 0.0114. And again, if you put it into your calculator there and did that math here, you would end up with a negative 0.00517, and you can't have a negative concentration. So that's how you know it's too big. Yeah. So remember that when you do get those two X values, in this case, we actually got two positive X values, but when you put one of those back into that equilibrium line, it will yield you either a negative concentration or negative pressure if you're dealing with pressures, and you can't have a negative either of those. Always be, yeah. Yeah, so a couple of ones we've done, I think we had like a positive, negative that came right out of the chute. So on those, it's relatively easy in most cases because like the negative is going to probably give you a negative number. But you can get, as we talked about, a positive and negative, positive and positive like we did here. And even I think I mentioned as well, you could actually get a negative and negative. But the end result of that is one of those values, when you put it back in that equilibrium line, will give you a negative number. Questions? Yeah. 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 These would be the equilibrium pressures. Yeah. Right. So as we can see, if we actually look at N2 and H2, there's not a lot of change in pressure, right? That means that pretty much everybody's hanging out still on that side, and we still have those gas molecules flying around. Yeah. Yeah, so we did that check because we made the assumption. So it should be automatic with you whenever you make that assumption that you should check it. And sometimes people, as we go through some more chapters, sort of forget the checking part of it. And there will definitely be times where it'll be more than 5%, and you do have to kind of go back and solve it a different way. So just make sure that you do check it. And sort of like 5% is sort of just a general, like, oh, it's acceptable. It's not that big of a change that's sort of happening. Yeah. Other questions? All right, so clearly you need to be able to do all this fun stuff. Yes. Come Thursday, probably for the quiz, I suppose. All right, so to finish up this chapter and talk about our friend Le Chatelier's principle here. And Le Chatelier's principle is basically this idea of you have a system that is at equilibrium, and you basically do something to it that messes it up. So remember that, as we've talked about, when we get a system that is at equilibrium, that means that the rate of that forward direction will equal the rate of the reverse direction in this case. And it basically will maintain that unless you do something to mess it up. And unless you do something which is sometimes referred to as adding a stress to the system. And there's a few different stresses that we could add to a system that's at equilibrium that will frankly mess up the equilibrium for a short period of time. But one of the nice things about the equilibrium sort of condition is even if you go and mess it up, it's going to want to once again get back to that equilibrium position. So you could screw it up for a short period of time, but it's going to kind of self-correct itself to get back to an equilibrium condition. So some of the stresses that we could do is we could do something with the concentration. So we could either obviously add or remove. We could do something with volume and pressure if we're dealing with gases. We could do something with temperature, which obviously we could increase or decrease, right? And we could also add a catalyst. So again, the idea here is we will have a system that's at equilibrium. It will kind of be messed up by the stress that's added, and it will try to once again get itself back into that equilibrium position. So we're going to talk about each of these things and sort of the effect it will have on a system that's at equilibrium. So why don't we start with concentration first here? So concentration, you can, as I mentioned, do one of two things. You could add more. And when we add more, typically what will happen is it will shift away. from the side that we added more to. So when we talk about shifting one way or the other with Le Chatelier's principle, we oftentimes talk about it shifting to the right, which basically means we're going to make more products. We could have it shift to the left, which basically means we're going to make more reactants. And lastly, there is actually a situation or two where even though you did something to it, it will actually cause no change to occur. So these are sort of your three options typically in a Le Chatelier's principle type question. Will it shift to the left? Will it shift to the right? And frankly, even though you did something, it may not actually make any type of change that will occur. Now, we can also remove. And when we remove concentration, it will always shift towards the side you removed it from. And when we talk about sides as well, we're really referencing the chemical equation, how it's written. So, if we add more reactants or we're adding more products, that's sort of what we're thinking about here. Clearly in the beaker, there is no kind of left side, right side. Everybody's just floating around. So when we talk about kind of left side, right side of the arrow, we're referring to the equation as to how it's written. So if we want to add more concentration, that's pretty simple, right? We could just go to the shelf and grab something that's in the equation and it has a source of it and just dump it in, right? So that is basically pretty simple. So if you needed to add more concentration, you pretty much grab a reagent. So for example, if you needed to add silver ions, you could grab some silver nitrate and that has silver ions in it and you can just dump it in and that would be like adding more silver ions floating around in your solution. We could remove things from a solution. How? Do we just reach into the solution and grab out the ions with our hands? No, no. We'll watch the safety video later. We do not do that, right? So never reach in with your hands, right, to grab anything. So how can we remove something that's floating around, like in a beaker that are ions? They're floating around, positive, negative ions floating around. How do we remove those things from a solution? Well, boil them off will not necessarily remove it, it'll remove the solvent, right? It'll get rid of like the water part of it, and then they will come back together and they'll actually just sit there in the solid. So when we want to remove something that's floating around, one of the things that we could take advantage of is the two things that are not included in the equilibrium expression, right? What two things do we not include in the equilibrium expression? Things that are solid, right? And things that are pure liquids. So what we can do, for example, is add another solution to this that has a negative ion that might react with the positive guy and make it a solid, right? And precipitate out that ion from solution. And that's effectively going in there and reaching in safely without your hands and taking out, right, that ion from the solution. It's going to be taken out of the equilibrium sort of expression and that's like removing it. So that's one way you can do it. That is a way you can physically see it happening, right? You can actually physically see the solid being formed and you could remove it in that particular case. Now, if we had something that maybe had, say, hydroxide ions floating around, right? I could add perhaps an acid, right? Because an acid's like H plus and OH minus will make water, right? Which is a pure liquid, right? And not involved in equilibrium. And by doing this, what we're essentially doing is reaching in there and grabbing out the hydroxide ions, right? Also, if you had an acidic solution where you had a lot of H pluses floating around, you could add a base, right? And do the same thing. This is one that you might not visually be able to see that you made water, but you can, that you're basically taking those ions out of solution. So those are really two ways that we could remove something from a solution and cause that change to occur. Questions on that there? Okay, so when we look at this here, let's just say we had a system at equilibrium. Classically trained artists here in stick figures 101. Actually, it's 102. That's advanced stick figures. They have faces here. So left-hand side here is our reactants. This is our products. Our system is at equilibrium. It's all happy. And now on the right-hand side here, somebody decides, hey, let's jump on that. And when we jump on that, what's going to happen in this case is something like this. So to fix this situation, right, we need more people on the left-hand side or right-hand side? Left-hand side, right? So we added people to the right-hand side. It's going to shift to the left, right, to fix that. And it's going to return to an equilibrium position here on the second time here in this particular case, right? And again, it will return back to the equilibrium position at that point. Now, if we had our same situation here, reactants and our products, and this guy decided, hey, I'm just going to jump off here. I'm going to go off. When that guy goes off, we're going to get this situation that occurs. Not so good here. So in this particular case, we need to put more people on the left or the right-hand side to fix this. We do, yeah. We removed over here, the equilibrium is going to shift towards the side we removed it to kind of fill the hole, if you want to think about it. We kind of created a hole there on the right-hand side, and it's going to basically come back once again to equilibrium here as well. So there is this sort of change that occurs in equilibrium. But what's really happening in these cases is, for example, here on the left, where we added more products, right? We now have a lot more products than reactants in this case, right? And that's going to cause the forward or the reverse reaction to occur. If you have more products, it should cause the reverse, right? And that's why it's going to actually shift to the left. That's also why when you would add more reactants, you would now have more reactants than products, which should cause the forward direction to occur away from the reactant side. And that's why it always shifts away from the side you add it to. When you remove something, you're essentially creating a hole on one side or the other. If you want to think about it that way, you got to kind of fill the hole if you want to think about it. But what's really happening in that case is if I remove products like I did on the right-hand side, I now have more reactants, right? Which is going to cause the forward direction to occur towards the hole I made, basically. And vice versa, if I removed reactants, that would essentially cause a hole on the reactant side, and I now will have more products, which would cause the reverse reaction to occur. So that's essentially what is truthfully happening here, outside of some wonderful stick figure drawings. Yes, any questions on that there? All right, so that's concentration. Add away. AA is a good way to remember that. Add away. And if you remove, it goes towards. Let's talk about then volume and pressure. And volume and pressure are oftentimes sort of tied together. And we remember this from our friend Boyle, perhaps. Boyle's law said, as the volume increases, what happens to the pressure? Pressure will decrease, right? Opposite relationship. So what's happening here is if we increase the volume, we will have a drop in the pressure. And what we actually want to do is kind of bring the pressure back up, right? Because that's the change that occurred. It kind of dropped out the pressure. So we want to bring that pressure back up. Now, in order to bring pressure back up, would I need to go to the side with less gas molecules or more gas molecules? More gas molecules, right? More gas molecules, more collisions, right? More collisions, more pressure. Pressure is going to come back up. So in this situation, it will shift to the side with more gas molecules. And that obviously is reaction dependent as to which side has more gas molecules. So you would count up all the guys got G's on the left and right and their coefficients, and you can decide which side is that. Opposite would be true here. If we lowered the volume, we're going to see a pretty sharp increase in the pressure because we're going to have a lot more collisions. So the change that's going to occur here, pressure is going to start to rise. We kind of want to bring the pressure back down. So to do that, we would actually need to shift to the side with the least number of gas molecules so we can have less collisions occurring. So for example, here, if we had a little 2A plus B goes to 4C in this case. All right, will these shift to the left? Will it shift to the right? Or will there be no change if I do the following things here? So let's start with, I'm going to add more C. I'm going to lower the volume. I'm going to remove A. I'm going to decrease the pressure. I'm going to add B. All right, so take a moment for each of those. Which way would we expect to look? All right, so if I add more C, which way should it go? Yeah, I added C, which is over here, which means when I add, it should go away from it, right? We're going to have more products, which means the reverse reaction is going to really take place and it should head to the left there. If I lower the volume, right, the pressure gets increased. And in a smaller volume, do I need more or less gas molecules? I do need less. And that's how I usually think about sort of volume pressures by the volume. So small volume, less gas molecules, larger volume, more gas molecules. So it's a good way to kind of think about it. So in this case, we just want to count out everybody that's G's here and their coefficients. So we got 3 gas molecules on the left and 4 on the right, which means in this case, we would also shift it there to the lower side of gas molecules. If I remove A, which way will it go? It will go to the left, right? Again, I'm removing A, which is creating a hole on this side. If you want to think about it, you got to fill that hole, right? So it's got to come towards it. R, again, really here, you'll have more products than reactants. So it's going to cause the reverse reaction to basically occur. If I decrease pressure, that means that my volume is going to increase. So I have a larger volume, more or less gas molecules. More, right? We're going to go towards the side that has more to fill that volume. And lastly, if I add B, it should go which way? Should go to the right, yeah. Again, we're adding more reactants, which means we have more reactants than products, should cause the forward reaction to occur. Yes. It
Your.
yeah, I'm gonna say yes, I think. My right or your right, whichever way. But yeah, so if this was like A and B on this side and this is C, if you added more B, it's gonna go that way, right? So it's got to come back this way. Bring it back. Other questions? All right. All right. So by the way, no change could occur in a situation with gases. What happens if I had the same number of gas molecules on each side? And I increase or decrease the pressure? Nothing. Yeah, it's a tie basically, right? There is no side that's more or less. So that's a place where you could get a no change that could occur. All right. So we did that. We did that. Let's talk temperature then. Temperature, which as we know is the only thing that will affect the actual value of the equilibrium constant. Temperature works the same as concentration, which means if you increase the temperature, it will shift away. And if you decrease the temperature, it will shift towards it. So how do we know which way is towards it and which way is away from it? It does depend on the type of reaction you're dealing with. So if you're dealing with a exothermic reaction, that means that heat and energy is released. And when we talk about a exothermic reaction, we think about energy, maybe not correct in all aspects of it, as being a product, like it is being given off, heat and energy. Most of the time, that would be thought of and given to you with a delta H value, which is our change in enthalpy. And for an exothermic reaction, delta H is positive or negative. It is negative. So I would say probably in most of these sort of Le Chatelier's principle problems, they will just give you the equation and give you a delta H value with it. And if the delta H value is negative, it doesn't matter really the number. If it's negative, it's exothermic. You could think of heat and energy as a product. That would mean that if I increase the temperature in an exothermic reaction, which way would it go? It would go towards reactants. It'd be like adding more products, and that would send it in the reverse direction. And obviously, if I remove temperature, like threw everything on ice, that would be like removing products, and it would go towards the product side. So again, that's how that works. Endothermic is pretty much the same idea, but opposite. That is when our heat and energy is absorbed. And when it's absorbed, we think of heat and energy as a reactant. Think of it over here. And much like our exothermic, our delta H here will be a positive value. And really the opposite effect will happen in obviously an endothermic case versus an exothermic case. If we increase the temperature of an endothermic reaction, it will shift away from the reactant side towards the product side, and we make more products. And if we lower the temperature of an endothermic, it will be like removing reactants, and it will come towards the reactant side. Any questions on that there? And again, I would say probably 9 times out of 10, this is how exothermic and endothermic is probably going to be presented to you in a problem as a delta H value, again, given to you. So really, again, just looking at the sign of that to know which sort of side to think about it. Any questions on that there? Lastly here, a catalyst. A catalyst, as we've talked about in the previous chapter, again, is not a reactant, not a product, and it does not get used up. Is there really, as we talked about, to sort of facilitate the reaction occurring faster? And the effect in terms of Le Chatelier's principle on adding a catalyst is typically you will get no change. You'll just get to equilibrium quicker. So that is another situation where you can get a no change that occurs. In addition, if you add like a noble gas, right? Noble gases are chemically inert, which means they're not going to react with anybody. So that's another way that perhaps a no change could occur. So something like that, adding a catalyst, or again, a tie on both sides in terms of the gas molecules are sort of common ways that you could get a no change to occur. Any questions on Le Chatelier's principle there? All right, so look at some of the examples you have here, and I'm just going to make up some. I'll just borrow the equations if I can find them. All right, so these are the things that we talked about. Again, concentration shift away if we add, go towards when we remove. K, again, does affect the equilibrium constant value, but really in terms of which way is going to shift, you want to determine exothermic or endothermic, and obviously our pressure that we talked about, either going to go more gas molecules with a larger volume, less gas molecules with a smaller volume. All right, so we'll steal this one here. Let's see what's happened. We'll just make this a make-believe that the delta H is definitely not this number, or maybe not even this sign, but we'll just use it for our example here. All right, so let's just say we have this. What's going to happen here? Are we going to the left? Are we going to the right? Are we having no change? If we do the following, we're going to lower the pressure. We're going to add H2. We're going to decrease the temperature. We're going to remove NH3. We're going to decrease the volume. We're going to increase the temperature. And we're going to add N2. All right, give it a go, see what you come up with for each of those. Okay, let's take a look here. So we'll start with lowering the pressure. When we lower the pressure, that means that our volume should increase. So we have a larger volume, which means we need less or more gas molecules. We do need more. In this case, on the left-hand side here, we got 4. Just adding the coefficients, basically. And on the right-hand side here, we have 2, obviously coefficients for anything that's a gas. So in this case, I think we would go to the left here. We're going to add H2, which is a reactant. That's going to increase really our reactance and cause the forward direction here away from it to basically occur. We're going to decrease the temperature here. This reaction is endothermic or exothermic. It is exo in my really made up one here. And that means that really heat would be more of a product. So in this case, we're going to decrease our products, which means really we have more reactants than products and we want to fill that hole. So it should shift towards it basically. We are going to remove NH3 in this case, which will cause the same effect to occur. We're basically going to cause a hole there on the product side that we need to fill. We have more reactants than products, so it's going to go towards that hole there to fill it. Any question on any of those there? We're going to decrease the volume. That should cause our pressure to increase. And in this case, we're going to have a smaller volume, which means we need less gas molecules. And that is going to be on the right-hand side here. We're going to increase the temperature. In this case, we already established it's an exothermic, so that would be like adding more products. Adding more products will cause the reverse reaction to occur, and it will shift away from it. And lastly here, adding N2 will add more reactants, causing the forward direction basically to occur and shifting away from the side we added it from. Any questions on any of those there? All right, we'll take a look at the last one. I think you got that was the same one. Take a look at that one here. And there should be a 2 there, just in case there's not. Let's go with, we're going to increase the temperature. We're going to add O2. We'll remove NO. We'll increase the pressure. We'll add a catalyst. And why not let us let's increase the volume. All right. Again, to the left. Let's take a look. So we'll start with increasing the temperature. So it tells us it's endothermic, which means my delta H should be a positive number. That also means that heat and energy should be a reactant or product. Should be a reactant. So now that when we increase our temperature, that would again be like increasing our reactants, which should cause it to go away and the forward reaction to basically occur in this case. We're going to add O2, which also is a reactant. So same idea, going to increase our reactants, going to go away from it because it's causing the forward direction to occur. We're going to remove NO in this case, which is our product. So we're going to decrease those. Again, if you want to think about it, you're going to cause a hole on that side. So you need to fill that hole. Also, really, you have more reactants in the product. So it's heading in that direction, basically. If you increase the pressure here, that means that our volume would decrease. So in that case, we would want to go to this side with the least number of gas molecules. In this case, which side is that? On the left-hand side, we have how many gas molecules? 2. And on the right-hand side, we have 2. That looks like a tie to me. So that is a no change situation occurring in this case. If we add a catalyst, it will no change as well. And lastly here, if we increase the volume, that means really our pressure is going to drop. We're going to go to the side in reality we want to, which is more gas molecules. But as we just saw, there is no more gas molecules. So that also would be a no change situation in this case. Any questions on Le Chatelier's principle there? Yeah. All right. That wraps up chapter 13, I believe. Yeah.